Okay, so this is the problem we left. You were working on it um, when we finished yesterday. So I told you there to answer this question. This is a question that I think has been on tests in the past. I took it off the test and put it in the notes just so that you would have a test question, um, along with A, and B, because A, B, and C are all the same question. They're just different parts, right? So part C of this um, is worth 4 points, would be worth 4 points if this was a test or a quiz. Okay. We talked about it yesterday. First thing, define the parameter. Okay. That's the first thing, numbers and words. The second thing that I would look for is assumptions and conditions because it comes from a sample of 10 females. Okay. The fourth thing is calculating the answer, or the third thing, sorry, is calculating the answer. And then the last thing is summarizing what that number means. Okay. So if this was a test or a quiz, these are the things I would look for. First thing is the true parameter. So we talked about this being a means question. We decided that for part A, right? We use that for part A. So it's a means question. So that means we need words and numbers to describe that. The true what? What does that describe? So we always start the true. There you go. Perfect. The true mean height of all women in the US. Okay. That's in words. Perfect. Do we know that number? Yes, we do. It's 64 inches, right? 64 inches. There's 1 point right there. 1 point right there for this question. Okay. Um, we our steps say label. Well, there's a couple other things they give us. They give us the population standard deviation, right? Oops. Okay. Sample size is 9 or is 10. Okay. You don't get points based off that, but it is important because we're going to use those things later. Some of them we've used, some of them we will use later. Okay. All right. So second thing is conditions or assumptions. Why do we have to check conditions or assumptions for this problem? It comes from a sample of more than one. Yeah. Letter A, there wasn't a sample. It was just one. This question involves a sample of 10. There are 10, a random sample of 10 females. Okay, so we got to check our conditions, our assumptions. So check. Okay, so the first one, SRS. Let's see. Is it stated? It's stated. Random sample of 10 females. Yep, stated. Okay. Next one is the 10% condition. That one says that n is less than or equal to 10% of big N. Okay. N is 10 for this one. Do we have a number for big N? No, we don't. So how would we describe big N in words? Yep. All females in US. All adult females, I should say. Yes. Pretty confident saying we're okay there. Yep. Right. Has to be bigger than 100? Pretty confident saying there are more than 100 US or adult females in the US. Okay. We don't have a number, so we don't put a number, but we at least label that. And the last one is normality. Yeah. So this one is a means question. question. So we don't look at this over here. We look at these over here. We have two options here. Option one, they told us in the prompt that the population is normally distributed. Or they didn't do that, but the sample size is big enough. Okay. So if we go back to the prompt, that's one of the things I highlighted at the very beginning and said, it's very, very important. That part's very, very important. This is why it is, because it fulfills one of my assumptions. Stated right there. Let me highlight it again. As normally distributed, roughly normally distributed. Oops. Okay. Done. So point here, point there. Okay. The next thing is actually calculating what the answering the question. What is the probability that their heights are greater than 67 inches? Okay. So we have a normal curve. What's the mean in the middle? What do I label the mean in the middle? 64, because that's the population parameter. That's a parameter mean. 67 or more. Yep, it's going to be to the right, shaded over here. That's the probability I want. So I need a z-score. So I go 67 minus 64 over the standard deviation. Do I put 3 there? No. No, I don't. I put 3 over the square root of 10, right? Because the standard deviation for samples is the population divided by the square root of the sample, or the number in the sample. Okay, so when we do that, what do we get?
3.16.
Okay.
Oh wait, the entire z-score?
The z-score, the entire z-score, yeah. 3.16. 3.16. Perfect. Okay. We go to our charts. What's the percentage that our chart says for 3.16? Yeah, it's pretty big. 0.9992. So that means our shaded part is everything else. So that is going to be 0.008 or 0.0008. Okay. That's the third point there. And then the last point is for summarization. Find out, tell me in as plain of English as you can what that 0.0008 number means. So if I was to change it to a percent, what percent would it be? 0.08%. 0.08%.
That's pretty good.
That's 8/100ths of 1%. Extremely small, right?
Yeah, it's not a zero.
It's not zero. It's not zero. It's not zero, but extremely small. Okay? So you can leave it as a probability decimal, or you can change it to a percent. Either way, we would say I'm going to leave it that way, probability
Does the number have to be in it, or could you just say that it's less than 1%?
There you go. You could say, to summarize it, it's pretty liberal to when you summarize it, because it's pretty much zero, right? So you can say less than 1%. You can say pretty much zero. That's fine. Yeah. For the explanation, as long as you kind of summarize, and that might be better because you're trying to put it in as non-technical terms as possible. So the probability of selecting a sample of 10 US adult females whose mean height is greater than 67 inches is 0.0008. And that's the last point. Okay. So the probability of reaching in and grabbing a sample of 10 women, taking their average height, and that average being over 67 inches is virtually nothing. Not going to happen. Right? So I have a question before we go on to the next one. Look at A. No. Yeah, look at A and look at C. Didn't they ask the same question? So if I randomly grabbed one female's name, the chances that that one female, her height is taller than 67 inches is about 16%-ish, right? But the probability I grab 10 females and find their average height, and that average is taller than 67 inches, is pretty much impossible. Not going to happen. Why is that? Why the differences? If it's asking pretty much the same question, how can you explain why 1%, one value is really, really low and one's not?
Because of the difference in sample size.
What does that do exactly? That
It lowers the variability, which means the numbers get a lot smaller.
There you go. As your sample size goes up, there's not so much, right? There's not so much variability. Variability goes down quite a bit. So now you're looking at something like that, right? Where there is none of this stuff over here. Can't happen. This stuff over here can't happen, right? That's why. So if I took a sample size of 100 women, what do you think would happen to this number here? It'd get even smaller, right? Because it goes back to that idea of, in the short term, anything can happen. In the short term, I could flip a coin and get 3 heads in a row. That doesn't mean it's 100% chance I'm going to get heads, right? If I were to do it 50 times, pretty close to 50-50 each. If I were to do it 100 times, pretty close to 50-50. The more I do it, the more the truth comes out, right? And that's what it's saying here. Okay. The bigger the sample size, the more chances that the truth is going to come out. And the truth of the matter is, the average height for women is 64 inches. Now, could I randomly pick a woman who's taller than 67 inches? Yeah. 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 There are tall women all over the place, right? But what are the chances that I could randomly pick 10 women and their average height is taller than 67? Now, in that group of 10, could I pick some tall women? Absolutely. But what's going to happen also? For every 1 or 2 tall person, I'm going to have 1 or 2 short people. And everyone's going to kind of balance out. Exactly. That's what happens as you get a bigger and bigger sample size. Okay? It balances out. One woman, very unpredictable. I don't know. Could happen. 16% chance, right? A group of 10 that their sample size is bigger than 67, not going to happen. Not going to happen. Okay? Unless this part is wrong. Unless this part is wrong. That's kind of what we're doing later, right? The next couple chapters, 8, 9, and 10, it's what we call hypothesis tests, which is testing that very thing, which is saying, hey, if I took a group of women and their height was 68 inches, their average height was 68 inches, what does that say about this claim right here? Exactly. That's a test. We test their claim. Okay. Well, that's the thing, right? It could be a statistical phenomenon, but if I take a sample of 10 and I did it right, then there can only be one answer. And that means that number's off. Okay. All right. Okay, the rabbit problem. All right, so I want you to do A and B. Do A and B for the rabbit problem. Okay, I'll give you about 10 minutes and we'll go over it. Just do A and B. If you finish A and B, you can go on, but just A and B for right now. So for A, we couldn't because population is stated as skewed to the right and the sample size is not big enough, right? That's why we could not, we would get a number, but it would not be accurate. We could calculate the number, but it wouldn't be accurate. B, on the other hand, we have a sample size that's big enough, so we can actually calculate the number and it will be accurate. Okay, so the second thing is we have to actually calculate it. So since it comes from a sample, we have to do our steps there. So mu, since it's mu, it's going to be the true, it's always going to start true mean. If it's a means question, if it's a proportions question, it's going to start true proportion. So what does this number represent? The true mean?
The true mean weight of the specific rabbit.
Yep, the true mean weight of this breed of rabbit. They didn't say the name, so we'll just say this breed of rabbit. And then they give us that number, right? What do they say? 5, yep. And standard deviation is 4. Yep. And then in this case, n is 35. Okay. Okay, that's 1 point. And we labeled everything we had. 3, check all assumptions and conditions because it comes from a sample of 35. So we have, anytime it comes from a sample, we have to check our assumptions and conditions. So assumptions, check. Number 1, SRS. Random sample, so we say stated. Good. Number 2, 10% condition. So is little n less than or equal to 10% of big N? Well, little n is 35. 10%. Do we have a number for big N? Nope. So what is the population? Not the parameter, the population. Who are the population? All rabbits of this specific breed. Or this particular specific breed. All rabbits of, let me make it a little bigger. This breed. Okay. And then the last one, well, we kind of answered the last one already, right? So how can we assume that the sampling distribution will be normal?
If n is greater than 30.
Since n is 35 or greater than 30, we can assume normality by, what is that called again?
The central limit theorem?
Yep,
Theory?
central limit theorem. Okay, that's 2 points. Next one, actually calculate it. So let's go actually calculate now. So the true mean is 5, and the question is asking what?
7 or less.
7 or less. So 7's over here. We're going to shade to the left. So let's see, let's calculate some z-scores. So n, oops, no. Z equals 7 minus 5 over, yeah, not 4, but 4 divided by the square root of 35.
So 2.958.
2.958?
Yeah.
So we'll say 96. Since our table only goes two places past the decimal, we'll go 2 places past the decimal. Okay, so we go to our z-score table, and what do we get?
9985.
9. Pretty high. Yep, pretty high, almost 100%. Almost near certain. Okay, the last thing is summarize it. Summarize that number. The probability of the probability that the that the weight, that the mean weight, mean weight of the sample, mean weight of the 35 rabbits
Less than 7 pounds.
that the mean sample is less than 7 pounds is 0.9985. Pretty close to 100% chance. So if I had all of these rabbits, if I were to label all of these rabbits, however many there are, label each of them, give each one a number, pick out a sample of 35 of them, weigh all of them. That average, find the average weight of all 35. The chances that that is less than 7 is almost 100%. Okay? The chances of that happening is almost 100% because the average is 5, right? Will there be heavy rabbits in my sample of 35? Yeah. But for every 35, for every 1 or 2 or 3 or 4 heavier rabbits, there'll also be some light ones, maybe some younger ones, right? But besides that, they're all going to be closer to 5, right? So that's what will happen. Variability goes down as sample size goes up. Right? Last two. If we were to take one sample of 80, so now we're raising it to 80. So if we take one sample of 80 of these same rabbits, what would the shape of the distribution of weights look like? So if I took a sample of 80, what would shape look like?
Roughly normal.
Well, yeah, exactly. Why roughly normal? Because our sample size is bigger than 30, we would assume that it would be normal or approximately normal or roughly normal. Okay? Since n equals 80, we would assume shape to be roughly normal. So that answers the question, and it explains why we say it's going to be roughly normal or normal. Because sample size is big enough. It's big. Okay. Last question. Describe the sampling distribution of the sample mean rabbit weights for a random sample of 5 rabbits. So now the sample size is 5 rabbits. So they want us to describe the sampling distribution. When they ask you to describe the sampling distribution, remember they're asking for shape, center, and spread. So let's start with shape. So based off a sample of 5 rabbits, what would be true about the shape? What would the shape be? So it would continue to be skewed right. Why? Skewed to the right because sample size is less than 30. Not big enough. Okay. Center. Still be 5. Spread. 4 divided by the square root of 5. Yep. 1 point something.
1.7888.
Yep. 0.7889. Yeah, eventually. Pounds. Done.
Nice.
Okay.
Why would the center still be 5 pounds?
Because that's what the it's stated as that. Where's it? Skip it right there. Because it would maintain these guys here. It would maintain this guy here. It would maintain this guy here. It wouldn't maintain this guy because this guy is based off of sample size. All right. Mm-hmm. Yep. Exactly. What if we had a sample size of 1? Plugged it into our formula here. What if we had a sample size of 1 here? It would just be the population, right? Yeah. It would just be the population. So that's why we say when we have a sample size of 1, it's not really a sample size because it's the same. as the population, right? As we get a bigger sample size, then it starts to become smaller. Okay. All right, so today is Wednesday, tomorrow is Thursday, and we have Friday. So what we're going to do the next 2 days is review. That's it. That's the chapter right there. We're going to review the next 2 days. Monday will be our group test. And then Tuesday, Wednesday will be our individual tests. Okay? So next 2 days, we're going to review. I'll assign an assignment. I probably won't see. I might post the assignment today. I might post it tomorrow because you have an assignment that's due tomorrow, right? You still have an assignment that's due tomorrow, so I probably won't post the last assignment for this tomorrow. We're going to do some in-class review as well. Okay, we'll start that tomorrow. Okay.